is Mr. Zou Yumin, who is the CTO of Shanghai JP New Energy Technology Company. He's going to talk about new PGM electrode in the field of hydrogen production. Today, I'm going to present to you, something about how to find new opportunities by utilizing PGM or the platinum group metals. Personally, I have over 30 years of experience working in this field, and mostly I was engaged in electrochemical things, so I will confine my presentation to innovation on this front. I'm going to share with you my experience. In the past, there have been a lot of industrial processes. I'm going to talk about how they come into being. And to be honest, there is demand, but luck is also very important. So you cannot neglect the factor of being lucky. But firstly, let me just give you a brief introduction of our company, JP New Energy. We supply all kinds of catalysts, and we use catalysts to compose slurry to produce stack. So for us, it's fair to say that we are a supplier of catalysts, but we also provide relevant services on the part of catalysts so that our customers can use our catalysts to their advantage. We have such products as cathode, anode, with or without carrier. But recently, we have also been engaged in alkaline stuff. In other words, we put precious metal on the surface of nickel mesh. As for water hydrolysis catalysts, of course, we have iridium oxide. All these things I'm going to cover in great detail later on. So it's fair to say that we provide one-stop shop services and solutions. In other words, we provide to our customers catalysts, but we also help them with CCM as well as suggestions regarding different working conditions. So this is an overview of the various catalysts that we supply. For platinum, carbon from 40% all the way to 100% in terms of cathode 20%, anode 20%, and we have graphitized carbon and have resistance to reverse poles. In terms of water hydrolysis, we use iridium oxide plus platinum as the anode. Later on, I'm going to cover this part in great detail. Well, this chart showed you something that happened in the past about 17 years, for about 70 years, how platinum catalysts were used in various electrochemical reactions. In the very beginning, platinum was used in DSA, or dimensionally stable anode. In the earliest phase of production of chloride, graphene was used. However, in this process, the chloride was consumed constantly. So by accident, some scientists from South Africa identified rhodium oxide, because usually metal oxides, they do not have electricity conductivity. However, there are two exceptions: iridium oxide and rhodium oxide. They represent something that were endowed to last by God. They're gifts to last by God, and the conductivity of rhodium oxide is only 1/10 that of iridium oxide, so the former is very special. So they use PAM as a separator. The industry thus prospered, but there are people who use precious metals such as platinum and rhodium as cathode. That's the second phase of development. But there is a third phase. The third phase features the use of iridium oxide as the anode, and on the cathode, you can collect various metals, including copper and including cadmium for electrolysis. The fourth phase is very special. Later on, I'm going to talk more about the details. So for JP, for our fuel cells for water hydrolysis, be it carbon or hydrogen, well, I'm going to talk about how everything turns from research into industrial process. So the first thing I'm going to talk about is something that you may not be familiar with. I'm going to talk about the hydrochloric acid water using electrolyzers, because there are a lot of such waste hydrochloric acid water. If you want to deal with it, you have to bury them on the ground, but they're expensive. So as early as the 1960s, some people start to think about how come that I couldn't turn waste water into something that's useful. In other words, I want to serve two purposes from this. On one hand, I can get rid of the waste. On the other hand, I can turn them into something useful. So in the 1960s, someone called Udi from Germany invented this process. They use cathode to generate chlorine, and they use anode to generate chlorine, whereas they use cathode to generate hydrogen. However, there are disadvantages to this process. On one hand, the pressure is high. On the other hand, there are risks of explosion because it's hydrogen in chlorine process. So they thought about why I can't do something similar to fuel cell. So there is a new process generated, which is called ODC. On the one hand, electrolysis process is there. On the other hand, they put them through the ODC process, or oxygen depolarized cathode. The catalyst of RHXS represents some sort of collaborative result between Bayer and Italian company called De Nora. So by chance, because De Nora, they bought Prototech from the United States, so they own. Well, by the way, you know that fuel cell mostly are related to PGM, so they invented this process. In 2001, I joined De Nora, the Italian company, and I started to study how rhodium sulfide could be turned into some important catalysts. Bayer, the company, worked together with De Nora, though the latter is much smaller than the former. But they have the determination and they believe that this process is very important. So in 2002, Bayer spent €2 billion and they put together a 30-member team. They work with the team that was led by me at De Nora, and it took us about several years. In 2003, it took us about several months. So in 2003, in Germany, there was a factory in place, and in 2008, in Shanghai, in Pudong area, they established another factory, followed by a new plant in Yantai city in Shandong province of China. So the process of rhodium sulfide was joint efforts between two companies with the same purpose of dealing with wastewater.
So this is a patent we were offered in 2005. We've applied for it global-wide. So the whole process basically uses redoxide sulfide and to use PEM to reduce oxygen as the anode. And then as the cathode is the traditional hydrolysis, then when combined, it's basically one stone, three birds. That means that we can treat the wastewater and turn it into the useful chlorine, which is the starting material for a lot of chemical industries. And also it saves electricity. It's very energy saving. So this is an example to demonstrate how to combine PGMs, new applications. And the second case is unitized regenerative fuel cells, URFC, meaning that we make one electrolyzer, but can be used for two purposes. One is as a fuel cell, and the other is for hydrolysis to produce hydrogen. So this actually responds China's demand for combining hydrogen production and fuel cells. So 2 in 1. So you have an anode and a cathode. For the anode is platinum, and for cathode, when it's producing oxygen, it is a cathode, but later on, for another purpose, it is the anode. So it's interchangeable. So I'm not sure if you can see it clearly, but that is how it works. Now I'd like to talk about alkaline electrolyzer. For alkaline electrolyzer to produce hydrogen, there's one big challenge, that is it's too big. So when you want to generate a lot of power, it's too big to be accommodated in any venues. So we need to reduce the size so that the electricity density can be reduced. Then what to do, how to achieve that? Then that is that we can turn to PGMs, because compared with nickel, it is more advantage, has more advantage in terms of electricity saving. And we can apply it on a nickel mesh that is 200 then we can save about 0.6 degrees electricity with every unit area of this nickel mesh. We can see that it's about 310 millivolts. This is what we've done in the lab. You can see that within 100 days, compared with the red starting line, we have this much energy saved. If you look at the left, it's a nickel mesh. And on the right, if you look closer, you will be able to see the coatings. It's actually very challenging technology because it's highly curved, so it's very difficult to coat. Then you will need to use electrochemical approaches to produce this stable coating. And this is a product for one of our clients. It's as big as 670 square centimeters. Another thing I'd like to talk about another case that is, as shown here, highlighted by yellow, that for this kind of iridium oxide plus water, and it is not as stable. So we're thinking about probably we can blend iridium oxide and platinum, things like this. And if you look at this graph, the black curve and the red curve, the black one is more stable, the red is more stable, and it's very clear that you can see which is a better choice. In 2010, inspired by this piece of literature, I feel that for iridium oxide, as it does not conduct electricity, so when you have 30% platinum, it will conduct electricity, so it can be more efficiently used. That's why we can see the results shown by the graph. If we use 2:8 or 1:9, this kind of platinum iridium oxide ratio, we can achieve stability, conductivity, and also durability. And also, we've looked at the application in our clients' projects. We can see that it's very good results, because usually we use 4 or 5 of it, but here we use the 6. This is another case. It is 2.5 milligrams per square centimeters. So compared with what we did in the past, that is the reliance on imported iridium oxide, I think our product is quite competitive. And if you look at the electrolyzer, the anode is the same. It's platinum and titanium. But if you look at the cathode, there is 5 milligrams of imported catalyst. And for our catalyst is 4 milligrams per square centimeters. So, but the results is a little bit less satisfactory. But in general, you can see that this kind of blended iridium oxide and platinum catalyst can help our client save a lot of energy and improve efficiency. So this is the end of my presentation. Thank you for your time.